Previously, we have converted the equations describing fluid motions into a rotating frame of reference, and we've used these to derive the geostrophic balance. This balance is the leading order dynamical balance of the oceans and atmosphere, and it is between the acceleration induced by the horizontal pressure gradients and the Coriolis acceleration, which is F times the horizontal wind. The geostrophic balance is apparent in weather maps, where the spacing between the isobars reflects the local horizontal pressure gradient. Where the pressure gradient is large, the wind speed is also large, and the winds are oriented so as to blow along the isobars, normal to the pressure gradient. Today, we look at a consequence of geostrophy. Specifically, we are investigating a phenomenon known as the Taylor-Proudman Theorem. Consider a flow in a rotating frame of reference with a small Rossby number and uniform density ρ. We write the horizontal components of the geostrophic balance in vector form, giving 2 omega cross u is equal to the grad of the pressure on density ρ. We now take the curl of this equation. The first thing to note is on the right-hand side. The curl of a gradient is 0, and ρ is uniform, so the entire right-hand side is 0, requiring that the curl of omega cross u is also 0. This can be expanded into these 4 terms. Now, omega is uniform, so the 2 terms with gradients of omega are 0. One term is omega times the continuity equation, which for our assumptions is 0, leaving us with omega dot grad u is equal to 0. Let's choose our coordinates such that omega is in the direction of z, meaning that the dot grad operator becomes the vertical gradient of u. This expands to du dz is equal to dv dz is equal to dw dz is equal to 0. Now, if there is anywhere in the domain that you know that w is 0, like a boundary, then because dw dz is equal to 0, w is 0 everywhere, and what you're left with is du dz equals dv dz equals 0. This is the Taylor-Proudman theorem. Physically, it states that horizontal velocities are constant with depth, and that the fluid moves as if it's infinitely skinny columns, known as Taylor columns. These columns align themselves with the axis of rotation. Let's take a quick look at the concept of the Taylor-Proudman theorem in the lab. Here we have 2 views from above and from the side of a tank that is in solid body rotation, such that the water is essentially at rest with the rotating tank. The particles behave as passive tracers at the surface of the fluid, so they move with the fluid. The dye reveals the flow through the rest of the depth. There is a small round obstacle on the bottom of the tank, here with a cross. We slightly perturb the tank rotation rate so that the water begins to move relative to the tank. For the water to flow over the obstacle, continuity requires that it have a non-zero vertical component of the horizontal velocity, which contradicts the Taylor-Proudman theorem. Now, as we see here, the obstacle, even though it is relatively small and on the bottom of the tank, it has a significant influence on the flow throughout the full depth, including the surface. The tracers resist flowing over the bottom feature and prefer to flow around it. But there is water above this feature, which is marked by the red dye, and we can see that it tends to remain there. That is, by way of the Taylor-Proudman theorem, bottom topography can affect the residence times of surface flows above topographic features.